Good morning everyone. Today we will discuss about carboxylic acid derivatives. Introduction. Carboxylic acid derivatives are a number of closest relative classes of compound which can be obtained by replacement of a OH part of a carbonyl group of acid by Cl, OOCr, NH2 or OR. The general formula of various functional derivatives along with their mode of formation from carboxylic acid are depicted below. Acid chloride, replacement of OH by Cl. Acid anhydride, replacement of OH by OOCr. Acidamide, replacement of OH by NH2. Ester, replacement of OH by OR. R and R dash may be represent simple or substituted alkyl or aryl groups. It may be noted that all functional derivatives contain the acyl group R C double bond O in their molecule and are therefore also known as acyl compounds. Structure of acid derivative. Acid derivative can be represented by general formula RC double bond O Y, where Y is equal to Cl O COR OR NH2. R and R dash may be the same or different. In all acid derivative, carbonyl carbon is sp2 hybridized. The third hybridized orbital lie in the same plane are directed toward the corner of a triangle at angle 120 degree with each other. These orbitals from third sigma point one each other oxygen group R and group Y. The remaining unhybridized p orbital of carbon overlap sidewise with p orbital of a carbonyl oxygen to form a double bond to give the structure. However, the atom of a group Y directly attached to carbonyl carbon has at least one lone pair of electron in a p orbital. This p orbital of an atom of a group Y may be also undergo overlapping with the p orbital of a carbonyl group to provide additional bonding as shown in figure 6.1. The actual structure of acid derivative may be best described as a resonance hybridized of a following contributing structure. Nucleophilic acyl substitution. Before discussing the different classes of acid derivative, it would be quite appropriate to have a look at a characteristic feature common to all these derivatives. This feature is that all acid derivatives participate in nucleophilic substitution reaction in which Cl, OC double bond OR, NH2, OR dash is replaced by other nucleophilic substituents. If the acid derivative are represented by general formula R dash C double bond O Y, where Y is Cl, OC double bond OR, NH2, OR dash, their nucleophilic substitution reaction may be given by the equation. Since the above substitution take place at the acyl groups, it is often referred to as nucleophilic acyl substitution to distinguish it from nucleophilic alkyl substitution met with in case of alkyl halides. Mechanism. Nucleophilic acyl substitution occur by a two-step additional elimination mechanism as depicted below. Step first, nucleophilic addition. As in the case of aldehyde and ketone, the carbonyl group present in acid derivative is highly susceptible to nucleophilic attack at the carbonyl carbon. This is of course due to ability of oxygen to acquire electron or accommodate negative charge. Therefore, step 1 of nucleophilic acyl substitution is similar to the nucleophilic attack on the carbonyl carbon of aldehyde and ketone. It involves the additional nucleophilic O to the carbonyl carbon to form a tetrahedral intermediate. During this process, the trigonal carbon sp2 hybridized of the acyl or a carbonyl group of a starting compound is converted into tetrahedral carbon sp3 hybridized in the intermediate. Step 2. Elimination of a leaving group. The tetrahedral intermediate formed in step 1 eliminate the group Y, originally present in acid derivative in the form of a negative ion, Y negative. Due to this elimination, the carbon-oxygen double bond is reformed and the substituent product is regenerated. The reason for the occurrence of this step is that the group originally attached to the carbonyl carbon in acid derivative are all good leaving group. For example, the chlorine atom of acid chlorides is an excellent leaving group and is readily eliminated as a chlorine ion as soon as tetrahedral acid addition intermediate is formed. In general, the case with which a leaving group is eliminated depend upon a basicity. The weaker the base, the better it would be a leaving group. In the nucleophilic acyl substitution of acid chloride, acid anhydride, ester, amides, the leaving group Y negative is equivalent to Cl negative, RC double bond OO negative, RO negative and NH2 negative respectively. Now Cl negative is a very weak base. RC double bond O negative is a moderately weak base, while RO negative and NH2 negative are strong bases. Therefore, the order of A's of leaving group is decreasing in order. Cl negative, R C double bond O negative, RO negative, and H2 negative. In conclusion, the complete mechanism of nucleophilic acyl substitution may be summed up as follows. The overall rate of reaction is sometimes affected by the rate of both the step, but generally it is the first step which is rate determining. Note: Step 2 of nucleophilic acyl substitution is in contrast with the reaction of aldehyde and ketones, where the initially nucleophilic attack is followed by the gain of a proton and not explosively of any group by the intermediate to form an addition product as shown below. If aldehyde or ketone were the undergoes nucleophilic substitution rather than addition, it would involve the removal of a hydride ion or alkyd ion R dash from intermediate, but these ions are amongst the strongest bases and therefore poorest leaving group. Accordingly, explosion of a H negative or R would be very different, and that is why aldehyde and ketone do not undergo nucleophilic substitution. Relative stability of acid derivative and their order of reactivity. Relative stability of acyl derivative. As stated above, acid derivative readily undergoes nucleophilic acyl substitution reaction. However, there is a large difference in reactivity of a different type of derivative toward nucleophilic substitution reaction. This can at least partly be contributed to resonance stabilization of a structure of a acid derivative. The structure of acid derivative RCOOY is a resonance hybrid of a three contributing structure as given below. The resonance from third is particularly important as it strengthens the bond Y and carbonyl carbon through significant double bond character and involve dispersal of positive charge on carbonyl carbon. In other words, their structure would lead to considerable resonance stabilization of acid derivative. Greater the contribution of a structure third, greater would be the stability of acid derivative. Amides are found to be the most resonance stabilized of all acid derivative because in them the positive charge in structure 3A, which corresponds to the structure 3 shown above, is borne by nitrogen. Since nitrogen is relatively less electronegative than oxygen, it can accommodate the positive charge more easily. As a result, the contribution of this structure becomes more important and it leads to greater resonance stabilization of amide. Esters and anhydride are similar stabilized by resonance but to a less extent than amides. This is because oxygen is more electronegative than nitrogen and cannot accommodate the positive charge easily. However, amongst ester and anhydride themselves, the structure 3B of ester is more stable than the structure of 3C of anhydride. This is because the structure 3B of ester, the positive charge on oxygen is somewhat dispersed by the plus I effect of group R, while the structure 3C of anhydride, the positive charge on oxygen is intensified by the minus I effect of a group in its neighboring neighborhood. Because more stable 3b make greater contribution to resonance hybrid of ester as compared with the contribution of a third C to a resonance hybrid of anhydride. As such, esters are more stable than anhydride. The resonance stabilization of acid chloride is found to be a list of all acid derivatives. This can be explained in terms of poor sidewise overlapping of a 3p orbital of a chlorine, in which the lone pair of electron is present with 2p orbital of carbon due to large difference in their size. As a result, the structure 3D containing the double bond between chlorine and carbon is not easily formed and does not make significant contribution to stability of resonance hybrid of acid chloride. Thus, the order of relative stability of a acid derivative is decreasing in order: amides, ester, anhydride, acid chloride. Order of reactivity of acid derivative: the order of reactivity of acid derivative toward nucleophilic acyl substitution has been found to be acid chloride, acid anhydride, esters, amides. This order is not only in accordance with the relative stability of acid derivative but can also be explained in terms of A's of attack as acyl carbon and A's of elimination of a living group as given ahead. First, electron deficient on acyl carbon. It is evident that the more the electron deficient or acyl carbon of acid derivative, better the site of a nucleophilic attack. Now, chlorine, oxygen, and nitrogen atom directly attached to acyl carbon in various acid derivative exert an electron withdrawing inductive effect on acyl carbon. This decreases the electron density at the carbon, but at the same time, all these atoms has an unshared electron pair which can undergo resonance interact with the acyl carbon, thus increasing electron density at it. This effect increases as we go from Cl to OC double bond OR to OR dash to ONH2. The net result is that acyl carbon of acid chloride has a minimum electron density and it goes on increasing as we move anhydride ester amide. Consequently, the acyl carbon of acid chloride is most easily attacked by nucleophilic and acid chloride are most reactive, followed by anhydride ester, while amide, acid amide, are least reactive toward nucleophilic attack. Second, A's of living group. The reactivity of acid derivative also depend upon the A's with which the living group is eliminated. The order of A's of living group, as already explained, is Cl negative, R C double bond O negative, R O negative, and H2 negative. This is in keeping with the observed order of reactivity. Interconversion of acid derivative by nucleophilic acyl substitution. Due to the difference in the reactivity of acid derivative toward nucleophilic acyl substitution, it is usually possible to convert a more reactive acid derivative into a less reactive one. For example, acid chloride being the most reactive can be converted into acid anhydride, ester, and amides, as discussed in the next session. On the other hand, amides being the least reactive cannot be converted into esters, anhydride, or chlorides. The possible conversion that can be carried out are summed up below. Role of acid catalyzed in a nucleophilic acyl substitution. Nucleophilic acyl substitution is catalyzed in the presence of acid. The H positive ion from the acid get attached to carbonyl oxygen. As a result, the oxygen can now acquire the pi electron of a C double bond O bond more easily. Consequently, the carbonyl carbon become even more susceptible to nucleophilic attack. Acid and alkyne hydrolysis of acid derivative. Hydrolysis of acid derivative is a typical nucleophilic substitution reaction of acid derivative. Its view of the mode of acid catalysis is in nucleophilic acyl substitution. It is not surprised that hydrolysis of acid derivative should take place much more rapidly in acid medium than in neutral medium. Mechanism of acidic hydrolysis. The mechanism of acidic hydrolysis may be depicted as Mechanism of alkyne hydrolysis. The hydrolysis of acid derivative is found to be catalyzed in alkyne medium too. This is because alkyne solutions species OH negative ion. This ion is naturally much stronger nucleophilic reagent than H2O, which is the attacking reagent in neutral medium. Thus, alkyne hydrolysis may be formulated as followed. Comparison of alkyl and acyl nucleophilic substitution. We have just discussed the nucleophilic substitution at the acyl carbon. The student has already studied nucleophilic substitution at alkyl carbon. As for example, in alkyl halide, it would be quite interesting to compare these two sides of nucleophilic substitution reaction. It has been observed that nucleophilic acyl substitution occur much more rapidly than nucleophilic alkyl substitution. For example, comparison with alkyl chloride and acid chloride is much reactive toward nucleophilic substitution. To account for this difference in reactivity at the acyl and alkyl carbon, let us compare the SN2 mechanism of nucleophilic alkyl substitution with the mechanism of nucleophilic acyl substitution. Nucleophilic attack on a tetrahedral alkyl carbon of alkyl chloride for intense, involving a highly crowded and unstable transition state containing a pentavalent carbon. However, a partially cleavage of a sigma bond must take place to follow the attachment of a nucleophilic to alkyl carbon. In contrast, the nucleophilic attack on a trigonal acyl carbon involves a relatively less intense transition state which change into a stable intermediate. Further, the attachment of a nucleophile to the acyl carbon requires the breaking of only pi bond of a C double bond O group, and the negative charge is accommodated on oxygen which can accept it readily. Thus, the greater reactivity of acyl carbon than alkyl carbon toward nucleophilic substitution can be well understood in terms of a mechanism involved in the two cases. It must be emphasized that even though carbonyl group present in acid derivative is retained in the product formed in nucleophilic acyl substitution reaction, it is largely responsible for the ace of formation of the intermediate. In other words, acid derivative owes their greater reactivity to the presence of a C double bond O group in their molecule. Acid chlorides. Acid chlorides are a derivative of a carboxylic acid in which OH negative part of a C double bond OH group has been replaced by a chlorine atom. Therefore, they have the journal formula R3OCl and are also known as acyl chloride. Nomenclature of chlorides. The name of acid chlorides are obtained by changing the suffix ic acid of a common or IUPAC name of corresponding acid to YL chloride. For examples, acid chloride having C double bond OCl group attached to a acyclic ring are named by adding the suffix carbonyl chloride to the name of parent ring. For example, cyclohexane carboxyl chloride. For compound containing some other group of a higher priority according to IUPAC nomenclature to additional to C double bond OCl group, the latter is treated as a substituent. For example, 2-chloro carbonyl benzoic acid. Preparation of acid chloride. From carboxylic acid, acid chloride are generally prepared by the reaction of a corresponding acid with thionyl chloride, phosphorus pentachloride, or phosphorus trichloride. For example, acetic acid plus thionyl chloride give acyl chloride plus SO2 plus HCl. From carboxylic acid salts, they can also be prepared by the action of phosphoric trichloride, sulfonic chloride, or phosphoric oxytrichloride on a sodium or a calcium salt of acid. For example, sodium acetate plus PCl3 give acetyl chloride plus Na3PO3. Physical property of acid chloride. First, physical state. Acid chloride are colorless hygroscopic liquid or a low melting solid having irritating odors. They fume in most air due to the formation of HCl by their hydrolysis. Second, solubility. They are soluble in organic solvents such as ether and alcohol. Boiling point. Since acid chloride do not contain acid hydrogen, they do not form hydrogen bond. According, they have low boiling point than their parent acid. For instance, acetyl chloride and benzoyl chloride boil at 324 and 470 Kelvin respectively, while the boiling point of a corresponding acid such that acetic acid and benzoic acid are 393 and 523 Kelvin respectively. Chemical properties of acid chloride. Acid chloride are the most reactive of all carboxylic acid derivatives. They readily undergoes nucleophilic substitution reaction characteristic of acyl compound and are easily converted into acid and other acid derivatives. The important reaction of acid chloride are discussed below. Reaction with nucleophilic conversion into acid and other acid derivative. First, hydrolysis conversion into acid. Acid chloride are hydrolyzed by water to form the parent acid. For example, acetyl chloride plus water give acetic acid plus HCl, while aliphatic acid chloride react vigorously with water at room temperature. Aromatic acid chloride react only slowly. Mechanism. The mechanism of hydrolysis of acid chloride with water may be summed up as followed. Second, reaction with alcohol. Alcoholysis conversion into ester. Primary and secondary alcohols and phenols readily react with acid chloride to yield esters. The reaction known as alcoholysis constitutes a very good method for preparing ester. Acid chloride plus alcohol give ester plus HCl. Generally, a base such as pyridine is added to remove HCl. Unlike some other method for preparing ester, this reaction is now reversible and therefore ester are obtained in good yield. Tertiary alcohol can form ester with acid chloride only in the presence of a base or an active metal like magnesium. Scott-Bauman reaction. Reaction of aromatic acid chloride with an alcohol or a phenol in the presence of a base such as aqueous NaOH or pyridine is generally known as Scott-Bauman reaction. Mechanism of this reaction has already been discussed under phenols. Third, reaction with ammonia and amines. Ammonolysis and aminolysis. Conversion into amides and substituted amides. Acid chloride reacts with ammonia and primary and secondary amines to yield amides and substituted amide respectively. The reaction with ammonia is known as ammonialysis, while the reaction with amines is known as aminolysis. For example, acetyl chloride plus ammonia give acetamide. Acetyl chloride plus ethylamine give N-ethyl acetamide plus ethyl ammonium chloride. Mechanism. In case of above reaction, the nucleophilic nitrogen of ammonia of the amine add to the acyl carbon. Then chlorine and one of a hydrogen from nitrogen are eliminated in the form of HCl, while combined with excess of ammonia and amine to form a simple or substituted ammonium salt. Fourth, reaction with carboxylic acid or their salts. Conversion into anhydride. Acid chlorides react with carboxylic acid in presence of pyridine or with the salt of carboxylic acid to yield anhydride. For example, acetyl chloride plus acetic acid in presence of pyridine give acetic anhydride plus HCl. Hydrochloride. Pyridine hydrochloride. The mechanism of reaction having already been given in chapter 7, the above reaction involves the replacement of hydrogen of water, alcohol, phenol, ammonia, amines and carboxylic acid by acyl group. According these reactions are all regarded as acylation reaction and acid chloride are known as acylating reagent. The acyl chloride is very good acylating reagent and benzoyl chloride is is benzoylating reagent. It may be noted that nucleophilic acyl substitution aromatic and chloride are less reactive than aliphatic acid chloride. This means that the acyl carbon of aromatic acid chloride is less electrophilic than the carbon of aliphatic acid chloride. Other reaction of acid chloride reduction when reduced with LiEAlH4 acid chloride are conveniently changed into primary alcohol. Second, Rosenman reaction on treating with hydrogen in the presence of partially poisonous palladium catalyzed decomposition on barium sulfate. Acid chloride undergoes partially reduction to form aldehyde. For example, benzoin chloride plus hydrogen in presence of palladium and barium sulfate give benzyl aldehyde plus HCl. 6. Reaction of organometallic compound. Acid chloride react with suitable cadmium compound to yield ketones. Acid chloride plus dialkyl or diaryl cadmium give ketone plus cadmium chloride. Acid chloride also react with Grignard reagent to form ketone. For example, acetyl chloride plus ethyl magnesium chloride give acetone plus MgCl2. But the ketone formed is acted upon further by Grignard reagent to yield tertiary alcohol. Friedel-Crafts acylation. Acid chloride reaction with aromatic compound in the presence of Lewis acid such as anhydrous ammonium chloride to form aromatic ketones. Aromatic compound plus acid chloride give in presence of anhydrous AlCl3 give ketone plus HCl. Halogenation of alkyne group in the presence of small amount of phosphorus acid chloride having hydrogen attached to alpha carbon undergoes halogenation at this carbon to form haloacid chloride. For example, propenyl chloride plus Cl2 in presence of phosphorus give alpha chloropropenyl chloride. In fact, Hell-Volder-Gillick's reaction of carboxylic acid is also believed to proceed by acid halides. Aromatic substitution. Aromatic acid chloride can also undergo the usual electrophilic substitution reaction of a benzene ring. However, C double bond OCl group has a deactivating influence the benzene ring and directing the entrance group to a meta position. Anhydride. Acid anhydride. Acid anhydride may be considered as derivative from an acid by removal of molecule of water from 2-carboxylic acid. That is nomenclature of acid anhydride. Acid anhydride are named by changing the word acid of a common or IUPAC name of a parent acid to the word anhydride. Preparation of acid anhydride. Reaction with acid chloride and carboxylic acid and their salt. Acid anhydride can be obtained by reaction with acid chloride with carboxylic acid in presence of a pyridine. For example, acetyl chloride plus acetic acid in presence of pyridine give acetic anhydride plus pyridine hydrochloride. In actually practice, sodium salt of acid is often used in place of a free acid. Second, dehydration of a carboxylic acid when heated in the presence of dehydration agent such as P2O5 carboxylic acid get dehydrated to form anhydride. For example, acetic acid in presence of P2O5 heat give acetic anhydride. 3. Acetic anhydride, which is by far the most important acid anhydride, is usually obtained on a large scale by reaction between acetic acid and ketones. Ketone plus acetic acid give acetic anhydride. Ketene is itself obtained by the dehydration of acetic acid at high temperature. Carboxylic acid in presence of AlPO4 and 975 Kelvin. Ketene plus water. Physical properties of acid anhydride. Physical state. Acid anhydride of lower aliphatic are colorless, sharp, smiling liquid, while aromatic anhydride are colorless, solid. Boiling point. The boiling point of acid anhydride are higher than those of acid. formed by their hydrolysis. Unlike carboxylic acid, acid anhydride do not form intermolecular hydrogen bonding, but the size of anhydride molecule is much compared to an acid molecule. This leads to a large van der Waals force attraction, which is responsible for higher boiling point. Solubility: lower member are somewhat soluble in water, but higher member are soluble only in organic solvents such as alcohol, ethers, and acetone. Chemical properties: acid anhydride, like acid chloride, undergoes nucleophilic substitution reaction typically of acid derivative. However, as already explained, acid anhydride are less reactive than acid chloride. The important reaction of acid anhydride are discussed below. Reaction with nucleophiles: first, hydrolyze conversion into acid. Acid anhydride are slowly hydrolyzed by water to form carboxylic acid. For example, acetic anhydride plus water give acetic acid. Second, alcoholysis conversion into ester. Acid anhydride react with alcohol to form ester. For example, acetic anhydride plus methanol give methoxyethanoate plus carboxylic ethanoic acid. Third, ammonialysis and aminolysis conversion into amides and substituted amines. Ammonia and primary and secondary amines react with acid anhydride to form amides and substituted amines respectively. For example, acetic anhydride plus ammonia give acetamide plus ammonium acetate. Thus, acid anhydride are also very useful acylating reagent. In fact, acid anhydride is one of the most widely used acylating reagent. The reaction: fourth, Friedel-Crafts acylation. Acid anhydride can also be used in place of acid halides in the Friedel-Crafts acylation of a aromatic compound to form ketones. Reduction: on reduction with lithium aluminum hydride, acid anhydride is reduced to primary alcohol. For example, benzoic anhydride in presence of lithium aluminum hydride HCO positive. Benzoyl chloride. Acid amides. Acid amides may be considered as derivative from acid by replacement of OH part of the carboxylic acid group by NH2 or NHR or NHR2 groups. They are further classified as primary, secondary, and tertiary amides according to the OHR part of a carboxylic group has been replaced by NH2, NHR, and R2 group respectively. Nomenclature of acid amides. Primary amines are named by changing the suffix ic acid of a common name and oic acid of a IUPAC name of corresponding acid by a suffix amides. For example, when C double bond OH NH2 common name form amide, IUPAC name methane amides. When amides group is attached to a cyclic ring, the compound is named by adding the suffix carboxamide to name of a parent ring. For example, cyclopentane carbamide. Secondary and tertiary amides are named as nitrogen substituted primary amides. The letter N is written before the name of the substituted group to indicate that the substituent is attached to nitrogen atom. Preparation of acid amide aminolysis of acid derivative. Acid amides can be obtained by aminolysis of acid chloride, acid anhydride, or ester. In actual practice, this method generally employed in aminolysis of acid chloride. Acid chloride plus ammonia give acid amide plus ammonium chloride. Second, thermal decomposition of ammonium salt. The thermal decomposition of ammonium salt of carboxylic acid yield amides. Ammonium salt give amides plus water. For example, ammonium acetate give acetamide. For example, third, partially hydrolysis of nitrile. Acid amides can also be prepared by partially hydrolysis of a nitrile by treating with concentrated HCl. For example, ethane nitrile plus water give concentrated HCl, give acetamide. Physical properties of acid amides. Physical state. Exception for form amide, which is a liquid. All other amides are colorless crystal solid at room temperature. Solubility. The lower member are soluble in water due to the formation of a hydrogen bond with water. Boiling point. Due to the strong electron intermolecular hydrogen bonding, amides have quite higher boiling point. Chemical properties of acid amides. Acid amides are not very reactive toward nucleophilic attack. This is because the electron deficiency at acyl carbon is somewhat made up by the resonance interact of a lone pair of the electron on nitrogen as shown below. Accordingly, acid amides are not used as acylation reagent. The important chemical properties of amides are discussed below. First, amphoteric character. Acid amides like amines may be expected to be basic character due to lone pair of electron on nitrogen. However, it is obvious from the corresponding structure given above that their pair of electron is not easily available for the protonation. As such, amides are only very weakly basic in nature. It may also be noted that due to partially positive charge on nitrogen, the hydrogen attached to nitrogen can be released as a proton in the presence of a strong base. Therefore, amides act as very weak acid as well. Therefore, when treated with strong acid or a suitable bases, amines can act as a weak basis or weak acid as illustrated before. Hydrolysis. Amines are usually hydrolyzed by heating with dilute acid and alkynes in acid solution. The product are a carboxylic acid and an ammonium salt, while alkaline solution yield a salt of a carboxylic acid and free ammonium. R3 double bond O and H2 give in presence of H3O positive give RCOOH plus NH4 positive. OH negative डालेंगे तो RCOO negative NH3. Mechanism. The mechanism of acid or alkyne hydrolysis of amines is similar to the general mechanism of acid or alkyne hydrolysis of acid derivative. Third, dehydration. On heating with dehydrating agents such as phosphoric pentoxide, amides and dehydrated to form nitriles. Acid amide in presence of P2O5 give nitriles. Reaction with nitrous phosphorus. Nitrous acid react with amide to form carboxylic acid and nitrogen gas. Nitrous acid is produced in situ by reaction between NaNO3 and a strong acid. This reaction is used for the conversion of amides to carboxylic acid, while the amides is usually to hydrolysis. It is also employed for the estimation of amides since nitrogen is obtained on the reaction of a quantity yield. Hofmann degradation. When treated with bromine and chlorine in an alkyne solution, an amides yield an amine containing one carbon atom less than the starting amide. The net result of reaction of elimination of a carboxyl group and the reaction sometimes also referred to a Hofmann haloamides reaction. The mechanism of reaction has been discussed later in chapter 10. 6. Reduction. On reduction with lithium aluminum anhydride, amides are reduced to amines. For example, acetamide give ethylamine. Ethers. Ether may be regarded as derivative of carboxylic acid in presence of OH. Part of a carboxylic group has been replaced by alkoxy group. Therefore, they have general formula R3 double bond OOR dash. Nomenclature of ester. The name of ester are obtained by writing the name of alkyl or aryl group before the common or IUPAC name of a parent acid and changing the suffix ic and oate for HCOOH, methyl formate, methyl methanoate. Preparation of esters. Reaction with the carboxylic acid and alcohol. Esters are generally prepared by direct esterification of carboxylic acid with alcohol in presence of strong mineral acids such as H2SO4 and oral Lewis acid such as BF3. The reaction is reversible in nature and is also known as esterification. For example, acetic acid plus benzyl alcohol in presence of H positive give benzyl acetate plus water. The mechanism of reaction has already been discussed in chapter 3. Second, reaction between an acid chloride or an acid anhydride and an alcohol. As already discussed, esters are formed by alkolysis of acid chloride and anhydride. For example, benzyl chloride plus ethanol give ethyl benzoate. In contrast to direct esterification of acid, the above method does not involve a equilibrium reaction and therefore esters are obtained in good yield. The mechanism of reaction has been discussed. 3. Trans electro esterification reaction. The reaction consists of alkolysis of ester in the presence of acid or a base when the alkoxy part of a repeating reagent displaces the alkoxy part of ester. Thus, one ester may be obtained by the other. For example, ethyl acetate plus N-butyl alcohol in presence of H positive give N-butyl acetate. Fourth, reaction of a carboxylic acid with a diazomethane. Diazomethane react with carboxylic acid to form methyl ethers and nitrogen. For example, the constituent a very good method of preparing methyl ethers as the reduction take place at room temperature and give high yield of ester. However, it may be pointed out that diazonium methane is a highly toxic and moreover it can be displaced and explosive violence mechanism. The reaction takes place in two steps. In the first step, a proton is transferred from the carboxylic acid to diazomethane to form a methyl diazonium cation CH3N2 positive. In the second step, the carboxylate anion, which is an nucleophile, attack the carbon of a protonated diazomethane, resulting in the formation of ester and explosion of a nitrogen SN2 process. Physical properties of ester. Physical state. Ester are colorless, pleasant smelling, liquid or solid. Solubility. They are in generally insoluble in water but soluble in most organic solvent. Boiling point. The boiling point of a methyl ethyl propyl ester are lower than those of a corresponding free acid. There is probably due to lack of a hydrogen bond formation amongst ester. Chemical properties. Like other acid derivative, ester undergoes nucleophilic acyl substitution reaction. However, as already explained, they are less reactive than acid chloride or anhydride. They may react of ester are discussed below. Conversion of acid and other acid derivative hydrolysis. Ester are hydrolyzed very slowly in neutral method. However, the hydrolysis being taken place much rapidly in acid or alkyl solution. Acid hydride of ester yield carboxylic acid and alcohol, where basic hydrolysis give alcohol and the salt of carboxylic acid. Since sodium salt of a higher carboxylic acid are used as the show of alkyne hydrolysis in known as saponification, it may be noted that in contrast to acid hydrolysis, alkene hydrolysis is not a reversible reaction. This is because the carboxylate anion formed in alkyne hydrolysis is more resonance stabilized than the carboxylic acid, and as such the former does not tends to react back with alcohol. Mechanism of alkyne hydrolysis of ether. The mechanism of alkyne hydrolysis of ether may be depicted as follows. Evidence of a favor of mechanism. It may be seen that alkene hydrolysis is a stepwise process consisting adding followed by elimination. This mechanism is well supported by the following evidence. First, kinetic studies. The reaction involved nucleophilic attack on the ester by hydroxide ion, and as such, the rate of a reaction should depend upon concentration of both the ester and hydrolysis ion. This is also in the same practice as the reaction found to have second order kinetics. Isotopic isotopic label study. It may be noticed that initially attack of a hydroxide ion take place at the acyl carbon, and it is the bond between oxygen of OR and acyl carbon which breaks subsequently. This type of cleavage is confined by isotopic exchange studies. For instance, when ethyl acetate, in which alkoxy group are labeled with O18, was hydrolyzed in presence of a base O18 appears in alcohol product and not in the acid salt. This would be possibly only for the cleavage between oxygen and acyl carbon, and not between oxygen and ethyl part of ethoxy group. Third, stereochemical studies. The alkyl cleavage is also supported by stereochemical studies of the alkyne hydrolysis of optical acid ester. Mechanism of acid catalysis hydrolysis of ester. The mechanism of acid hydrolysis is the reverse of the described for the acid catalyst esterification. This is because all the steps in acid hydrolysis as well as esterification are reversible. For the mechanism may be depicted as follows: as evidence in favor of the mechanism. Here again, isotopic label studies have been confined that the acidic hydrolysis involves the cleavage of the bond between oxygen and alkyl carbon. This is evidence from the following example. Comparison of acid and alkyne hydrolysis. The acidic and alkyne hydrolysis of ester differ from each other in two main respective. In acid catalyzed hydrolysis, the acid is required in very small amount because it acts only as a catalyst. On other hand, in alkyne hydrolysis, base is required in equimolar amount because it is on of a reactant and not merely a catalyst. Second, acid catalyzed hydrolysis is reversible while alkyne hydrolysis is irreversible. Second, aminolysis. Ester reacts slowly with ammonia to yield amides and alcohols. Mechanism. The reaction involves the attack by nucleophilic nitrogen of ammonia on the alkyl carbon. This is followed by elimination of alkoxide ion and hydrogen ion to yield an amide and an alcohol as shown below. 3. Alcoholysis of a trans-esterification. It has been already mentioned that on reaction of an ester with an alcohol, the alkoxide part of a reacting alcohol displaces the alkoxy part of ester. This reaction, also known as alcoholysis or a trans-esterification, take place in the presence of an acid H2SO4 or a dry HCl or a base alkoxide ion of the replacing action, and is used for convenient one ester into another. This is a typically nucleophilic alkyl substitution reaction in which the attacking alcohol acts as nucleophilic reagent. Since the reaction is an equilibrium reaction, the attacking alcohol must be used in a large excess to shift the equilibrium toward the right, or else on the of the product should be stimulatively removed from the reaction mixture. Mechanism of a base catalyzed trans-esterification. This may be depicted as follows. Mechanism of acid catalyzed by trans-esterification. The mechanism of trans-esterification is the presence of acid may be outlined as follows. It may be noted that these mechanisms are analogous to those of base and acid catalyzed hydrolysis discussed earlier. Other reduction. Esterification can be reduced either by catalytic hydrogenation or by the chemical reaction to form alcohols. On one molecule of ester yield 2 molecules of alcohol, one molecule being derivative from acid part of ester and the other from the alcoholic part. However, these two molecules may belong to the same or different alcohol. Catalytic hydrogenation. This is carried out by treating the ester with hydrogen at amount 525 Kelvin or 200 to 300 atmospheric pressure in the presence of copper cumarate catalyze. Ester, ester plus hydrogen in presence of copper chromate give ethanol plus methanol. Ethanol plus alcohol. The reaction is often referred to an hydrogenalysis as it involves the cleavage of ester by hydrogenation. It is not surprising that under the condition of catalyzed hydrogenation, the ethylene linkage present in the ether are also reduced. B. Chemical reduction. Ester can also be reduced to form alcohol and sodium and alcohol Bovient blank method or with lithium aluminum hydride. An advantage of using these reducing agent is that ethylenic reagent, if any, present in the ester remaining intact. For example, methyl laurate in present sodium and C2H5OHQ lower alcohol. Fifth, reaction with Grignard reagent. Ester other than those of formic acid react with Grignard reagent to form tertiary alcohol. The reaction probably take place through the intermediate reaction diketone. The reaction substituent an excellent method for the preparation of tertiary alcohol. It may be noted, however, that two of the three alkyl or aryl group attached to a carbon carrying the hydrolysis group of a tertiary alcohol formed are derivative from the Grignard reagent. As such, as alcohol formed must have to least toward identical alcohol or aryl group. Ester of formic acid HC double bond OOR containing a hydrogen in the acid part and as such give rise to secondary alcohol reaction with Grignard reagent. Mechanism. The mechanism of reaction may be summed up as follows. Reaction with hydroxyamine. Ester react with hydroxylamine to form hydroxymic acid. The hydroxymic acid form deep red color complexes with the ferrous salt. This constituent a useful test for the detection of ester group. Calcium condensation. Calcium condensation involves the condensation of ester molecule presence of a strong base such as ethoxide ion and give rise to a beta ketone ester. For example, condensation of two molecules of ethyl acetate in presence of sodium ethoxide give rise to acetoacetic ester. Mechanism. The generally accepted mechanism of a calcium condensation is as follows. The epoxide ion abstracts a hydrogen ion from an alpha carbon of ester to form a resonance stabilized carbon anion. This strongly nucleophilic carbon anion attacks the carbonyl carbon of a second molecule of ester. The resulting anion eliminates an ethoxide ion to form the ketoester. The ethoxide ion finally removes a hydrogen ion from the ester to form the anion which is obtained in a form of a sodium salt. Chemical analysis of a carboxylic acid derivative. The functional derivatives of acid are best characterized by their hydrolysis. On hydrolysis, an acid derivative form a carboxylic acid either in the free state or in the form of an alkyl salt, and not product which depend upon a class of acid derivative. This other product can be made use by recognizing the nature of a given derivative. Thus, first acid chloride are hydrolyzed by water to liberate HCl, which readily form a white PPT, while alcoholic solution of a silver nitrate. Second, acid anhydride are hydrolyzed by slowly by water to form only carboxylic acid. Third, acid amides are hydrolyzed by boiling aqueous alkyne to form sodium salt of acid and ammonia, which has a characteristic smell. Turn red litmus blue and form a reddish-brown PPT with natural reagent. Fourth, ester are hydrolyzed in presence of an alkyl to form an alkyl salt of carboxylic acid and an alcohol or a phenol. Complete identification of a given acid derivative is possible only if the product of hydrolysis are completely analyzed and identical. Thank you. This chapter is complete.